Hello, everybody. I hope you're well. It's my pleasure to be presenting at TQC 2021. And I hope there'll soon be the opportunity to meet again in person. So as you can see from the title of the slides, I'm going to talk about dynamical entanglement, which means the entanglement for states. And this is a work done in collaboration with my colleague Gilad Gour at the University of Calgary. So to start, we need to acknowledge that entanglement is a resource because we can do stuff that otherwise would be impossible, like teleportation, dense coding, and so on. And the reason why it's a resource is that because it allows us to overcome some constraints. And in particular, we know that the constraint associated with entanglement has some sort of local nature, local in quotes. And the idea that something is a resource can be formalized and quantified precisely using the formalism of resource theories. So where we have a subset of allowed operations. In the case of entanglement, the standard subset we study are LOCC protocols or LOCC channels. The idea is that here we have some parties. In the simplest case, we have two parties that perform local operations, so in their own lab, and they exchange classical communication between them, for example, to share the outcome of a certain measurement performed in a certain lab. So here you can see a pictorial representation of what an LOCC channel looks like. So we have Alice and Bob, denoted by A and B. Alice and Bob perform some local operations in their labs, and then they exchange classical communication, which is represented by these dashed arrows. And for example, in this case, Alice transmits the outcome of her measurement to Bob, and Bob, according to that outcome, chooses something to do. Right. The key thing is that the definition of LOCC channel is very physical, very physically motivated, because it allows us to essentially capture the essence of entanglement. However, these protocols are very complicated to study. And I'd like here to reference this paper just because of the title, everything you always wanted to know about LOCC channels, but were afraid to ask. So this summarizes, I think, with a good title, all the difficulty of approaching this set of channels and studying the transition between states that are allowed by these channels. For these reasons, other researchers have proposed ideas of generalizations of LOCC channels, which are easier and more tractable. And a particularly simple one is the set of PPT states and associated PPT channels introduced by Rains. So the idea is that in this case, everything that is free, so not a resource, is given by PPT. By a PPT condition, and in particular, free states are PPT states. So how do we define them? So maybe many of you know this stuff quite well. However, I think this slide is actually very important because this will be the guideline for the generalization from PPT channels to PPT super channels we're going to present in this talk. And you'll see that essentially the construction will be identical to the one I'm introducing here for states. So let's first of all define the transpose operation, which is of course the transpose. And we say that a bipartite state rho AB is PPT if when I apply the transpose only on one party, Bob's party, that's why it's called partial transpose, I get another state. And free operation are called PPT channels. So how are they defined? Essentially, a channel is PPT if when I pre-compose and post-compose Bob's side with a transpose, I get still another valid channel. Now, let me explain the notation here. So you see here that I have an AB. So this denotes a bipartite channel, as we're going to see also later. So to keep a notation that's close to the one for states, I'm going to actually represent each let's say, the input and output of each party with a single letter. So actually A denotes two systems, one system as input and one system as output, similarly for B. So when you see the subscript 0, it means that this system is the input, and when you see the subscript 1, then you see that the system is the output. So in this case, this means I'm applying first the transpose to Bob's input, then I apply the bipartite channel, and then I apply the transpose again to Bob's output. And I get still a valid channel out of that. So this type of resource theories and of operations are actually easier to work with, but for every good thing, there's always a price we have to pay. And specifically, the price we pay is that this theory is very, let's say, it's very large, very broad, even too broad, because now some PPT states are entangled. So this is actually quite a crude approximation of entanglement theory. Okay, so after this brief recap of the entanglement theory for states, then we are ready to introduce what is necessary to go beyond the static formalism for entanglement and study what's necessary for channels instead. Okay, so as I said, entanglement theory, at least the ones that has been considered so far, has been studied systematically only for static resources. For dynamical resources, we still have some works. However, I think that we still need some systematic study and some deep study of that type of theory. And in particular, what we need to do, we need to move from static resources states to dynamical resources. Why do we need to do that? Not just because of mathematical curiosity, but actually this is really important because even the first protocols I cited, teleportation, dense coding, what they do, they actually transform a state, an entangled state, into a channel. So in other words, we want to have a framework in which entanglement is treated in a flexible way such that states and channels are analyzed and treated on the same grounds. And to this end, we need to understand, therefore, how to manipulate channels or how to manipulate states to get channels. The key tool in this respect is the notion of a superchannel. So what's a superchannel? It's a linear map, as always. And what the superchannel does, it sends quantum channels to quantum channels in a complete sense, in the very same way as a quantum channel sent quantum states to quantum states in a complete sense. What do I mean by this? This is a more technical definition, so which also allows me to define and specify my notation better. So when you see in this talk Gothic characters, it means they are super channels or super maps. When you see script, instead, it means they are channels or other maps. And the action of a super channel on a channel is denoted by square brackets instead of round brackets. Okay, so what happens here is that, what does it mean in a complete sense? It means that I have my bipartite channel NRA. I'm going to apply the super channel only to the A system, so A input and A output, and on the rest I'm not going to do anything. So I'm going to apply this Gothic I, which is the identity super channel. And if I do so, if something is valid, is a valid super channel, I should get another bipartite channel as output, another valid bipartite channel as output. Okay, so far this looks like abstract algebra, but in fact this is not the case, because superchannels can also be realized in a laboratory. Indeed, they can be realized using a structure called quantum cone. In this case, we call it one cone because there's only one hole. What is that? So we have a pre-processing F1, and then we have a post-processing F2, and then they are connected by a memory system E0, and then there is a hole where I can plug my channel N, which I want to, let's say, transform using that super channel. In particular, this structure is very convenient in the case of resource theories because it gives us the most physically motivated type of super channels in the context of a resource theory. Because if we take F1 and F2 to be free operations of a certain resource theory of states, then what we construct here is a well-defined free superchannel, which we call freely realizable because it can be realized using free channels, a free pre-processing and a free post-processing. However, we can also consider other types of superchannels. For example, in the very same way as we defined completely resource non-generating channels, which this is what CRNG stands for, we can define also CRNG superchannels. The idea is that a CRNG superchannel transforms free objects, free channels to free channels in a complete sense. Okay, that sounds cool. And the question is, what's the relationship between freely realizable superchannels and CRNG superchannels? So a freely realizable superchannel is also CRNG. It's not hard to show. But then we can ask the converse question. So if I have a CRNG superchannel, is it true that it's freely realizable in terms of CRNG channels? So in other words, do I have a free CRNG pre-processing and a CRNG post-processing with which I can realize and implement this CRNG superchannel? We don't know. This is actually quite a big problem in the resource theory of channels. And actually, this is one of the key points of our work, because essentially in our work, focusing on CRNG superchannels rather than on freely realizable CRNG superchannels allows us to get a higher simplification in the treatment, in the mathematical treatment of the resource theory. Okay, and as I announced, they are actually easier. So now we have all the tools in order to start the exploration of the theory of entanglement for channels. So our object of interest is a bipartite channel. What does it mean? It's a channel that has two inputs and two outputs shared between Alice and Bob. So we have a space separation between Alice and Bob and also a time separation between the input and the output. Again, the most physically motivated type of superchannels are freely realizable LOCC superchannels. They are the most physically motivated for two reasons. First, because LOCC channels are actually the most physically motivated types of channels, okay? So these are LOCC channels. And then, secondly, because freely realizable superchannels are also the most physically motivated free types of superchannels because they can be constructed out of free operations. Okay, and as in every resource theory, we try to answer the key question, which is the interconversion problem. So is it possible to convert one channel into another? So here we approach the problem in two different ways. The first way is by defining a complete family of monotones. This is how they are defined. These are those monotones E sub P of NAB. So this is how they are defined. So I need to fix P sub A prime B prime, which is a channel. Now, the systems A prime B prime will become clear what they are in a minute. So for the time being, imagine that we know how we choose A prime and B prime, okay? So this is how we define those monotones. We take the Choi matrices of P, okay? That's the first Choi matrix we consider. Then we consider another thing. We apply an LOCC superchannel to N, which is the F of N here, right? And we consider the Choi matrix of that expression. And then we take the Hilbert-Schmidt inner product of these two Choi matrices. Again, I probably didn't say it explicitly, but J means Choi matrix of those, of the channels in the superscript. Okay, and then I optimize this over all possible LOCC superchannels. So in other words, I apply all possible LOCC superchannels to N, and then I evaluate this Hilbert-Schmidt inner product, and I take the supremum of these values. Okay, so this quantity is actually computable with a conic linear program. However, since we are working with the theory of LOCC, and in this case, we are working with a topological closure since it's not a closed set. This conical linear program is actually a hard one. But nevertheless, it's notable, and we can formulate our conversion theorem. So now, suppose we need to convert NAB into MA prime B prime. So now you understand that A prime and B prime are the systems of the target channel we want to consider. And then we know that it's possible to achieve a conversion in the topological closure of LOCC if and only if for every channel P in the target system A prime B prime, I have this inequality between these monotones. So essentially the value of the monotone on NAB is greater than or equal to the value of the monotone on the target channel. Okay, and that's the first result. We can also approach the problem in another way by introducing the conversion distance. So how is defined? Again, I apply all possible LOCC superchannels to NAB, okay, and then I consider the distance of this of the output of that superchannel to the target channel M sub A prime B prime. Okay, so target superchannel. Sorry, target. We apply superchannel to the initial channel, and we calculate the distance to the target superchannels, and the distance calculating the diamond norm, and we optimize. We take the infimum over all possible LOCC superchannels. Okay, so clearly the conversion is possible again in a topological closure if and only if this conversion distance is 0. But this conversion distance also allows us to consider imperfect conversion, so conversion up to an epsilon when we fix arbitrarily. Again, this is a conic linear program, but since we are working with LOCC, it's actually a hard one. The question then becomes that maybe instead of working with LOCC, as we did in the case of entanglement for states, we can move to consider the generalization of PPT channels, which are PPT superchannels already envisaged by Leong and Matthews. So how do we proceed in that case? The definition is actually very, very similar to that for PPT states. Remember, for PPT states, we introduce the transpose map. Here, we introduce the Gothic T, which is the transpose supermap, which is, let's say, whose action is just applying the transpose at the input and at the output of a channel. So now notice that the definition of a PPT channel is very similar to the definition of PPT state, because now if I apply the transpose supermap to Bob's side of the bipartite channel and I still get a valid channel, then my channel is PPT. And similarly, we can define PPT superchannels in a very similar way as we define PPT channels. Do you remember? We pre-compose and post-compose with a transpose map. Here, we pre-compose B here, and we post-compose B prime with the transpose supermap, the Gothic T here. And if we still get a valid superchannel, then we say that the superchannel is PPT. We can actually prove that this definition is well posed because these PPT superchannels are also CRNG for PPT channels. So they send PPT channels to PPT channels in a complete sense. In particular, they are a superset of LOCC superchannels. The good thing about this is that now, if we calculate the complete family of monotones and also the conversion distance, they become easier because they become SDP, so easily computable and no longer a hard conic linear program. Okay, and the key thing here is that actually we considered CRNG PPT superchannel. We didn't consider freely realizable PPT superchannel, which means PPT superchannel with a PPT pre-processing and a PPT post-processing. So since we just work, let's say, on a global level, if you want to take that expression, this was actually the reason why we could find such simple expressions. And this also suggests something else, says okay, if the resource theory of NPT entanglement is easier than the LOCC one, even for channels, okay, so maybe we can also get monotones that are more easily computable from the NPT resource theory, and then we can also apply them in the LOCC case, because again, LOCC are a subset of PPT. The first one we consider is the negativity, which was introduced by Vidal and Werner. And again, so how did we generalize it? Very simple. So we replaced the transpose map with a transpose supermap, Gothic T. We replaced the one norm with a diamond norm. Okay, but this is not the end of the story, because we still need to check that this monotone, this candidate monotone, is actually well defined, and indeed it is, because we prove that actually it's an NPT monotone. So we still need to prove it. We can't just like generalize and hope that everything works. And there is another one which actually plays some role and is directly inspired by the notion of kappa entanglement introduced in a paper by Wang and Wilde. The expression of this monotone is actually quite complicated. And I give it here to you to show. I don't want to spend too much time on it. Again, J is the Choi matrix. And here where you see only P sub A0, B0, this means that we have traced out A1 and B1. Okay, so otherwise we would just write A and B. Okay, so we can prove that this is an additive NPT monotone, okay, under tensor products, and it's also computable with an SDP. So, but why do we care about this? Because it has some operational interpretation. Here I give you a simplified version of this operational interpretation because it's actually slightly more technical than this. The idea is that essentially what we want to do, we want to study how much entanglement we need to simulate a certain number of copies of a channel NAB, that are simulated in parallel, so tensor product of those, out of E-bits, so the maximally entangled states. And we require that this simulation is carried out through PPT super channels. So here we have a PPT channel. And we also require that for every n, so for every number of copies of the target channel we want to prepare is exact. And asymptotically, when we take the limit as n goes to plus infinity, we find that the cost is actually equal to this max logarithmic negativity we introduced in the previous slide. So after the cost, we turn to the dual problem, which is the distillation. So how much E-bits, how many E-bits can we distill out of many copies of a channel? Specifically here, we consider a PPT one. Because again, we want to see whether we can still have the generalization of the statement for PPT states by the Hordetsky's, where we can have no distillation out of PPT states. Now there is a slightly, slight complication, let's say, because when we have n copies of a channel, we can combine it in different ways. So actually the most general way to combine them is using an adaptive strategy. So because we can put them in parallel, let's say, prepare independent of the other, but actually the most general strategy is this one, where essentially these copies are plugged into the holes of a big comb, like in this case. And in particular, we're interested in a PPT comb. Why a PPT comb? Because it's actually the most general type of comb we can think of, which also covers the case for entanglement. That's for LOCC entanglement, I mean. So how does it work in this case? So how can we recognize a PPT comb? We can recognize because if we take the composition of all these realizations here, this realization of the comb, then what we get here is a PPT channel. Okay, if that's the case, then we have a PPT comb, or alternatively, the Choi matrix of this comb is also the Choi matrix of a PPT channel. As I said, this gives us the most general distillation strategy. They are simpler to deal with mathematically because they only involve partial transpose, let's say. And the key thing is that they can give us upper bounds in the theory for all possible theories of entanglement, and specifically for the LOCC case, which is the most interesting one. And what we find is that actually, due to, let's say, properties of the partial transpose, is that it's not possible to distill any maximally entangled states out of PPT channels using any sort of adaptive strategy, whether LOCC, separable, PPT. Okay, because essentially, again, we show that this distillation is zero using a PPT adaptive protocol. Therefore, it must be zero also using an LOCC adaptive protocol, because LOCC is a subset of PPT. And in particular, this allowed us to find also an example of a bound entangled POVM. So let's go to the conclusion. So what we did, we developed a rigorous theory of entanglement for channels using resource theories. We focused in particular on NPT entanglement because it was simpler to deal with and allowed us to give us meaningful bounds and also new measures of dynamical entanglement. And we also discovered the phenomenon of bound entanglement for channels. Here, there is actually a lot to be done, because we still need to explore the whole area of dynamical entanglement. For example, the hard part, the LOCC theory in the dynamical case. So also what happens in the multipartite case. Here we only focus on the bipartite case. Do we have interesting phenomena? And again, there's still the whole zoo of measures of dynamical entanglement to be explored. And with this, I'd like to thank you for your attention, and I'll leave you with some references.